weekly sessions to explain yeah, so I take these weekly sessions as kind of tutorials to explain some questions related to the week material and some other hands-on examples as well. So today is week 4. We're going to deal with optimizers, right? uh, all kinds of stochastic gradient descent, the different varieties of gradient descent, how they differ from each other, how they work basically, uh, and how we have improved the methods of optimization. Right. So the way that I normally do the sessions is that I will please mute yourself. Yeah. So the way that I normally do the sessions is I will introduce a problem, and then I will give some time to solve it, and after a while I will explain the solutions of the problem, and we'll cover a multiple number of problems like this, and eventually after we finish all the problems I'm going to show a little small hands-on kind of demonstration about uh, optimi optimizers, right? How different optimizers can impact the learning of your model, for example, right? It will be like a short example, but we'll see how things work, right? So let's start off. It's we're revising a little bit about uh, gradient descent, right? Which is the heuristic that we use to train these models, these networks. Very simple question here. Which of the following is or are true with movement in a contour map? So contour map is basically like a lower dimension projection of something that is higher dimension, right? Typically, it is a 2D projection of a 3D surface, right? And it marks areas with the same altitude as like these contours, right? So the question, of course, doesn't actually specifically deal with contour maps. It just deals with gradient descent, right? Or the idea of gradients and gradients in general, basically. Right. So hopefully this should be very easy to answer. You can post in the chat if you have answered, if you want to answer. And I'll just give like a minute. We'll move on to the next question. I will explain and then we'll move on to the next question. Right? I'll briefly explain. Let's see. Okay, no one has answered. But anyways, this is a very, like I said, this is a very simple problem. The solution is in the name itself, right? A gradient is something that captures the slope. So if the gradient is small, then it's a gentle slope. if it is a if gradient is large, then it is a steep slope, right? So gradient is nothing but the slope expressed in different terms, right? So gradient is nothing but dy by dx. Yeah, so like I said, gradient is nothing but the dy by dx is the, and specifically the gradients that we are going to deal with is will be with respect to the loss function, right? And in the previous session we had seen some examples of loss functions, and we had also seen some examples of how uh, gradients can be computed for different loss functions, right? So yeah, one thing I would like to specify is that over here I am using dy by dx, but in reality what we will be using are the partial derivatives. So it is like del y by del x, which is the partial derivative of y with respect to x, right? Not the total derivative, right? So like I said, uh, it can be helpful to think of these loss surfaces in terms of contours, right? Because it is a lower dimension projection of a higher dimension surface. It is for the same reason as to why contour maps exist. You know, topological uh, maps exist, right? Because they give you broad understanding of the lay of the land, right? So contour maps, you know, for loss surfaces are nothing different. Uh, so here we have some examples, right? So this is a, let's say the loss looks like this. It's a two parameter thing, right? And you know, it's like a parabola kind of shape, right? So this is your loss surface, right? And I'm showing it as a one projection, but essentially what this actually is a three-dimensional surface, right? And you can imagine that, you know, you just project this, you just spin this projection around and you'll get something resembling the the entire loss surface, right? So something like that, you can imagine it in that sense. uh, the important thing is that this is just a projection, right? And then we can take slices out of it, right? So this slice is at one point at the loss of the loss. This is slice one, and this slice is at another point uh, at the loss, right? So this is slice one and slice two, and then we are trying to represent these slices, right? So this is a 3D kind of information that is being presented. We are trying to present it, represent it in a 2D plane with contour lines, right? And the question is, which of these four contour lines actually correspond to the situation being shown over here, right? So once again, I'll give a couple of minutes for everyone to work it out, and then I will explain what is happening. Okay, so Okay, so a couple of people have answered, and in fact, this is the correct answer, right? C is the correct answer, obviously. So we'll briefly let us understand what is happening over here, right? Essentially, a you're drawing these contour lines at these predefined values of loss, right? So the contour line for 2 is going to be drawn for when the value of loss reaches, whatever this value is. Let's say this is L2, let's say, right? So we can say that this value of the loss is L2, and similarly we can say that this value of the loss is L1, right? And obviously L1 is higher than L2. And the other thing to notice here is that the loss surface is shaped in such a way that L1 will be encompassing L2 completely, right? So it will be completely surrounding L2, right? So the only one option that matches this description is option C, which is why it is the correct answer. The other thing is that obviously, option B is kind of, they're disjoint contour lines, which is not the case, as we can see over here. Option D is a impossibility because they they depict contour lines for different values of L, right? So they cannot intersect at any point, right? Because that would mean that at these intersection points, the loss value is both L1 and L2, which is not possible. And A is obviously not correct because, as we see from the figure, L1, the contour at L1 is supposed to completely overlap the contour at L2. So that's why A is right. So yeah, so we have this, right? Very hopefully everyone is clear. So we move on to the next. So this one we'll briefly talk about. Actually, we'll have a couple of questions dealing with momentum based techniques, right? And is momentum is one of the earlier kind of modifications of the basic gradient descent technique, right? So typical gradient descent, in typical gradient descent, you would just have this last term, right? So you'd have learning rate eta multiplied by the weight update delta w t, which is like at the tth step of gradient descent updates, right? And you just have update t is equal to this, right? Learning rate multiplied by uh, delta w, which is nothing but negative of the gradient of the loss with respect to the weight, right? And then for momentum, uh, we do a very simple change to this, wherein we just add an extra term which looks at the previous update that was carried out, right? So for update t, we look at update t minus 1, and we multiply it with this thing called as the momentum value, right? Gamma is the momentum term. It's a hyperparameter, and typically gamma is set to be less than 1, right? So you can set it very high. It's usually set to some value like 0.9, right? So you set gamma to 0.9, or whatever you set your learning rate to whatever kind of value that works best, and then you let this go, right? And uh, so here is the question basically. So the question is like, why would we want to do this, right? And the question here is like, which of the following is true? That history is never taken into account. Does it take? B is a restatement of A, right? Uh, C is C is stating that you are only considered about concerned about history. D is saying that you are combining history with the current gradient, right? And this should not be difficult to figure out which one of these is correct, right? Anyways, I will give a minute, see if other people answer, and then we just briefly talk about momentum a little bit, and then we move on to other kind of optimizers, right? Okay, so yeah, so obviously from the discussion, it's clear that D is the correct option, right? We take the, and it should be clear from just looking at the uh, equation itself, right? Essentially, what you're doing is that you are looking at the previous update, right? And you're adding some fraction of that previous update to the current. And what it is doing is that if there was a direction in which the gradient was moving previously, right? Then this is going to have like a it is essentially going to have exactly what the name implies, right? It will have a momentum in that direction, right? It will have a bias towards the direction that it was going, uh, the the direction in which it was going in the past, right? And then it will basically make a larger uh, movement, right? And essentially, the reason why you do this is that it kind of helps to speed up your convergence, right? So your network can converge, the learning of the network can converge faster because you're going to make a kind of big, uh, somewhat bigger uh, updates to the weights. And of course, there is a problem associated with it as well, which we'll see later, and how successive iterations of this algorithm were developed to kind of deal with those problems, right? So yeah, like I said, take a larger step because you account for the history as well, right? And that has that has exactly a momentum like effect, kind of pushes your weight update in the direction that it was already going, right? So, yeah. So then we come to like what I was saying. Obviously, momentum is useful, right? It helps your training converge faster, but it also has its own problems, which are exactly because of the way it makes the training converge faster. right? And then people developed what is called as Nesterov accelerated gradient, which is a modification of momentum, and it tries to solve the problems of momentum, right? And so this question is about uh, what problems does Nesterov accelerated gradient actually solve, right? So I will give a couple of minutes once again for people to think about this problem, try to recall what MAG does, and contrast it with how momentum operates, and answer the, the question, right? So you can put it in the chat and see if you want to share your answer. Okay, so uh, yeah, C is correct, but C is only partially correct, right? So the deal with momentum, like we explained previously, is that it had this momentum, right? So it was uh, whatever direction the gradient was going in the previous step, that direction was basically added to the current step, and that made it converge faster. But it also had this problem where basically it would overshoot uh, the minima position, right? So because there is a momentum term, it is likely to overshoot. And what happens when it overshoots is that it has to then come back, right? So this overshooting and then returning phenomenon causes what is called as oscillations, right? So basically the answer, the model basically kind of oscillates around the optimal condition, and over time the oscillations become smaller, and then you get your kind of good optimal solution, right? And a related problem, of course, is that if your oscillations are too big, you might overshoot the minima value altogether, and you end up in a suboptimal kind of situation, right? So Nesterov accelerated gradient basically tries to solve both of these problems, right? And they are not independent problems, the problem of momentum, right? The problem of this additional push causes oscillations, which can also cause the problem of in escaping the minima value, right? So they are kind of related problems caused in a sequential chain, right? So one causes the other, and then that causes the third problem, right? So basically, correct answer is C and D, right? Both of this. And the way that Nesterov energy actually tries to account for these problems is that it's a very simple algorithm. It essentially just looks ahead, right? So it applies the history part of the update uh, in the starting itself, right? And then it computes all the outputs and gradients with that updated weight, and based on that, it tries to compute what is the update that needs to be carried out, which already has a kind of baked into it the fact that you're going to apply this history, right? So the update corrects whatever was the wrong part of that history update, and you get smaller oscillations. You get greater kind of staying within the minimum value, right? So it stays within the minimum value, more likely to stay within the minimum value, right? So yeah, and this part, uh, so here we are basically just kind of looking into the algorithm for energy instead of accelerated gradient, which I have already explained just now, right? So you have three possible algorithms that might, one of these actually represents the pseudocode for energy instead of accelerated gradient. You have to figure out which one it is, right? So yeah, so this is going to take a couple of minutes. Try to read through the code and try to understand what is happening, right? And try to figure out which one is actually the correct algorithm. Ah, nice. Someone has answered. It's good to see. Just wait for one more minute and then I will explain what is happening in each of the pseudopods. Uh, okay, so we have one answer and so it is in fact the correct answer. B is the correct answer, right? So let's go through what is happening in each of these pseudopods, right? In the first pseudopod, uh, we are starting, we are applying the forward pass on the weights directly. WT basically refer to the weights at the time step t. Sorry. Okay, let me see what is happening. Mm. Let me see. Settings. Settings. Yeah, sorry, microphone had changed. Hopefully now you can hear me again, right? Uh, mm, okay, okay. Yeah, so like I said, um, yes, so starting with option A, right? We do the forward pass with the unchanged weights, right? Then compute the loss and gradient. Right? Obviously, you do the forward pass and then you'll do the backward pass for the loss and the gradients. And then you do something which is kind of silly over here. You compute the look ahead weight and then you compute the update as this, right? And then you apply this update, right? Which is doing nothing essentially, right? So because your forward pass and backward pass have already happened with the original weights, so this look ahead weight is adding nothing. It is entirely superfluous, right? We are not even using this value over here, right? So this is actually just momentum, right? So here, essentially what you're doing is you're computing the update with respect to with this gamma times update t minus 1, and then whatever update you have calculated in this current step, and then you're applying that, right? So this is basic uh, basic momentum with some misdirection thrown in between, right? So this is wrong. Then what is happening in option C? Why is this wrong? Right? If we see why C is wrong, we can understand why B is correct, right? So first step is fine. We are computing the look ahead weights by applying the history, right? Historical update, which is the previous step update with this momentum term gamma, right? Then you are performing the forward pass and loss and gradient with these look ahead weights, right? So you're using the history, you're using the look ahead weights to compute forward pass and backward pass, you compute the gradient, right? Which is exactly what you want to do under nested of accelerated gradient. And then you are computing update. So until here, both of these are identical. Uh, the only difference is that when you are updating the weight, when you're generating W of t plus 1, is the weight for the next step, here you're doing WT minus update t, right? Which is update t over here. Here you're doing W look ahead minus update, right? And this is not correct because W look ahead already has this history term accounted for, right? Because W look ahead was already WT minus gamma times update t, and then there's another gamma times update t in this update, right? So when you apply this, essentially what you are doing is you are applying 2 times gamma times update t, right? as the history part of this update, and then whatever was computed by the look ahead, right? So this will also kind of negate the idea of energy, because in energy you had basically considered that the history part has already been applied in the beginning, and then the forward and backward pass has been computed, and then based on that you are getting the update, right? So if you apply the history part again after all of this, then obviously that is wrong, right? Because this double 2 gamma times update t minus 1, this level of history momentum was not actually uh, what you mitigated by this forward and backward pass, right? What you mitigated by this forward and backward pass was the effect of single gamma times update t minus 1, right? So if you do that, you're kind of losing the advantage of the energy. So obviously this is actually the proper algorithm for, or rather the proper pseudocode for energy, right? And later, I mean, after we finish all of these questions, uh, we will see kind of a small example, right, where you can appreciate the effect of all of these differences, right? So we'll see that later, right? So this is energy, right? Then we'll move on briefly. So this energy was, so that is one type of optimization, right? But there are two different levels of how you kind of choose to optimize, right? So there is one thing, you can decide what kind of gradient descent you are going to apply, right? And broadly speaking, there are three kinds that you might have learned in the lectures as well. One is what is called vanilla gradient descent, which is also simply known as gradient descent often, right? Which is like it is the older conception of gradient descent, basically from the time when we did not have this explosion of data, right? And this neural network types methods where the main kind of idea is that you feed a lot of data and then you learn from that data, right? So the old kind of gradient descent basically uh, comes from a time when data was kind of limited, right? Then you have stochastic gradient descent, and finally you have something which is in between these two, right, which is called as mini batch gradient descent. And typically mini batch gradient descent is the one that is used everywhere, right? For whatever model you might be training using deep learning, that is what is going to be used, right? So with that out of the way, let's see this question. uh, so there is a data set with 1 million points, right? And the question is, with vanilla gradient descent, if you go through this data set 3 times, how many updates are going to be carried out, right? So I will give like a minute for people to try to answer this. uh, it's very simple if you know what these terms mean, uh, right? It's very straightforward. Yeah. So like I said, this is a fairly straightforward problem if you know what these terms mean, right? So like I was saying before, vanilla gradient descent is from a time when before this kind of idea that you will do data-driven model optimization, right? And basically the idea earlier was that you look at the entire data set, and based on the entire data set you compute a gradient, right, to update the weights of your model, right? So vanilla gradient descent essentially, if you ran through, irrespective of the size of the data set, if you run through the entire data set once, it will generate one update, right? So irrespective of the fact that there are a million points in this data set, if you run through it three times, it will only update your weights three times, right? And the problem with this, the kind of reasoning behind doing something like this was the fact that the gradient that you are kind of estimating, right? So it is just an estimate, right? And uh, the quality of the estimate will become better and better if you have more and more samples from which you estimate the gradient, right? So that was the idea behind doing gradient descent like this. But of course, it is incredibly slow if you have, if you have a large amount of data on which you want to train your model. This will be this will be very slow, right? So entire whole epoch it will just update the weights once, and even if the quality of the gradient is very good, it really doesn't matter, right? It will still be very slow to converge. So this is something that is not at all used nowadays, right? So you can safely forget about this odd way of doing gradient descent after this part of the course. The other thing, this is what is it's actually used, right? So we consider mini batch gradient descent. The dataset size is n. That means there are n samples total, and the mini batch size is p. So the question is how many updates are performed in one epoch, and one epoch is a kind of a technical term. It just means that you are going through the entire dataset one time, right? So we're going through all the n samples. uh, yeah, so once again, I will just give a minute for people to kind of answer this because it's fairly straightforward once again. Okay, so yeah, like I said, this is a fairly, again, once again, very straightforward question if you know what these terms mean, right? And the answer, of course, is n by b, right? And so it's like I said, it is very clear once you understand what is mini-batch gradient descent, right? So for mini-batch gradient descent, instead of for vanilla gradient descent, we are considering the entire dataset for computing to compute one gradient. For mini-batch gradient descent, we basically consider the mini-batch, right, or the batch, and we are given that the mini-batch size is b, right? So basically, we consider b samples to compute one gradient and then one update, right? And the total data set size is n. And the way that mini batch gradient descent actually works is that you take non-overlapping batches to cover the entire data set, right? So the number of batches that you are going to uh, cover, the number of batches that you're going to uh, perform while going through the entire dataset once is of course n by p, right? So you divide n by p, that many number of batches can be generated from this dataset. So that many number of updates will be carried out when you go through uh, the entire dataset once, which is one epoch, right? So yeah, mini batch gradient descent performs one update for every mini batch, and there are n by b mini batches in this dataset, obviously, right? The other extreme of obviously when you're going from when you're going from vanilla gradient descent to stochastic gradient, I mean mini batch gradient descent, uh, the accuracy and stability of the gradient estimate suffers, right? Other extreme of this thing is stochastic gradient descent, uh, which if you have gone through the, which is kind of a misnomer actually, because even mini batch gradient descent is very often called as stochastic gradient descent in the actual literature for this for deep learning, right? So typically you say any kind of um, non-optimized, uh, non like without kind of special gradient descent, like without Adam optimizer or something like that. All of those things you typically just call it as SGD or stochastic gradient descent, right? Even though kind of the term is not fully accurate, right? Uh, the way that stochastic gradient descent actually kind of works is that stochastic gradient descent considers the case where mini batch is mini batch size is one, right? So you just consider one sample for every update, right? So you start with stochastic gradient descent on a given data set, and obviously, you have your mini batch size is one, the quality of the updates is not great, right? It's a very noisy update that you're going to apply. So there is a lot of oscillation, right? To improve this, or at least try to improve this, we can implement mini batch gradient descent. And the question is, what happens to the accuracy and stability of the gradient estimates, right? So you go from a case where you are estimating the gradient based on one sample into a case where you are estimating the gradient based on, let's say, 100 samples, right? And the question is, what happens to the accuracy and stability of the gradients? Right. So obviously, you can guess uh, what is the correct answer, right? It's not very difficult. Uh, in fact, it is quite obvious that when you go from stochastic gradient descent, where you estimate based on one sample, into mini batch gradient descent, where you estimate over number of samples, your uh, stability and accuracy of the gradient estimate should increase, right? And I mean, it's a fairly intuitive kind of thought that it should increase, right? So, but why does it exactly, right? So here we can consider a very simple experiment, right? So, which this is nothing but like a restatement of statistics, theorems and statistics, right? Regression to the mean, essentially, right? Essentially what you are going to do is that they are both of these methods are attempts to estimate the true gradient at any given point, right? And they are corrupted with noise. And uh, typically the way you solve the problem of noise is that you take multiple samples and then uh, the average out whatever readings that you get. Essentially what it does is that it reduces the composition, reduces the part of the noise, and uh, makes your estimate more accurate, right? And an easy way to kind of understand this is, you consider a coin which lands on heads with a certain probability, right? If you try to estimate this probability p based on one single coin toss, it's going to be a very bad estimate, right? Because the coin will either land on heads or it will not land on heads, so you're going to end up with either 0 or 1, right? But if you perform like 100 coin tosses and then try to estimate p by the average of that 100 coin tosses, then you'll get a value that is very close to p. If you do 1,000 coin tosses before estimating the probability, then you'll get an even better estimate, right? Closer and closer to the true value of p, right? So with this, so basically this hopefully kind of says why you would want to get out of stochastic gradient descent and into mini-batch gradient descent. Uh, there are other reasons also which deal with how these networks are actually executed on deep learning hardware, for example, like GPUs and stuff, right? So, but we'll see that more clearly in the kind of hands-on example, right? Which will show a couple of things. Right. So with that, we have reached the final question that I would want to discuss here today. One is, so this one deals with a couple of optimization techniques called ADGRAD and RMS prop. And essentially, so this ADGRAD was, one of the optimization techniques, and it had a problem that it would get stuck, right? And then RMS prop was proposed to deal with this problem of ADGRAD getting stuck. And the question is, how does RMS prop actually uh, achieve this thing, right? How does it prevent this ADGRAD optimization technique from getting stuck before convergence, right? And if you know the equations of ADGRAD and RMS prop, if you have access to them, you can go back and see, and you kind of it's kind of easy to figure out exactly why this happens, right? So yeah, so I'll give again a couple of minutes and then we'll see the solution and we'll explain, and then uh, we'll have a brief kind of, I will give like a brief hands-on kind of thing to explain a couple of the concepts, to showcase a couple of the concepts that we saw today. Mm. Yeah, so okay, someone has answered, and yeah, that is in fact the correct answer. So we'll just briefly look at the equations for both of these optimization techniques, right? And then we can, and by looking at these equations, we can figure out what's wrong with AdaGrad, right? So in AdaGrad, basically, you compute this VT term, right? Which is, if you look at it, this VT is VT minus 1 plus the square of the gradient, right? Computed at time t. And essentially what it means is that this VT is always a positive quantity. In fact, it is a positive, it's not guaranteed to be non-zero, but yeah, it's always going to be positive. And essentially what will happen is that as you go, so you increase the number of optimization steps, it will become higher and higher, right? Because at no point is this value reducing, uh, right? And then what you do is you uh, normalize the learning rate by square root of this VT, right? And of course, there is a epsilon term here which is there to avoid division by zero, right? So epsilon is there only to avoid division by zero, but essentially what you're doing is that you're dividing this learning rate by increasing number at each step, right? And it just keeps going higher and higher. So at some point, this epsilon basically goes to zero, right? And when epsilon goes towards zero, you cannot get any update no matter what your gradient actually says, right? So this is why it was getting stuck. And the way Adgrad solved, or rather, the way RMS prop solved this problem was simply by changing this equation. Instead of having like a direct sum uh, of the history and the square of the current gradient, you have a weighted sum, right? So it's beta times v of t minus 1 plus 1 minus beta times the square of the gradient, and this term can basically go up and down, right? Depending on the values of beta and the history term and the current gradient, right? And that that itself, that correction, that uh, value correction was sufficient to kind of make, so if you see, the final equation is identical in both of these. The only difference is that is how you compute this VT term, right? And by making this decay term less aggressive, it solves the problem, right? So it no longer gets stuck before convergence, right? So with that, we have come to the end of this. Let me join here. Okay, so yeah, so we have and separate. Let me share the screen again. uh yeah, so we are screen should be shared now. So what I will do is, yeah, so Okay, very good. So this is a so this is, if you don't know, this is a IPython notebook, right? Which is a standard way of kind of doing this kind of work, like a small Python script. Then you can break it into chunks, and then you can execute it in chunks, right? And this is nothing but Google Colab, uh, which is like a web-hosted cloud server that you can access, right, for free, and kind of run code on the GPUs there, right? So we will reconnect. Uh, so here the code that we are using is very good. So here what we are doing is we are using TensorFlow and Keras to define our network. You know, you're grabbing the dataset from TensorFlow datasets and running the code. TensorFlow is not the only framework that you can use. TensorFlow is one of the frameworks that you can use. The other one, which is more popular these days, is PyTorch. You can use PyTorch as well. Hopefully, I will have some PyTorch examples as well. This is a very simple example. Uh, you start off by importing all the relevant libraries. We have TensorFlow, we have NumPy, we have Keras. So Keras is kind of a wrapper on top of other background libraries like TensorFlow and PyTorch, where Keras helps you build your deep learning models without much complication, right? So it makes the process of building models simpler. Uh, and then get TensorFlow datasets, TFDS, uh, where TFDS is kind of an online store of datasets, where you can benchmark datasets, where from where you can grab something and kind of test your model against, right? So yeah, so first thing here that we are doing is uh, generating this dataset, right? So we are loading tfds.load. We're loading the MNIST dataset, which is handwritten digits, splitting it into train and test, and yeah, and then I'm displaying here like 4 examples, right? So yeah, so this is just a display function, right? And these examples show exactly how these samples look like, right? So these are 28 by 28 images. They're black and white, right? Single channel. And they have these handwritten digits, right? So you have like 4, 1, 0, 7, things like that, right? The next part of this is we want to normalize these values, right? Uh, so the MNIST dataset is stored as images, right? And images typically represent their colors by 8-bit numbers, right? So whatever value that you can see here, these values kind of they go from 0 to 255, right? So what we do is we normalize them, right? And we convert them from unsigned integers to floating point values, right? Because our network expects floating point values. So yeah, so essentially so what we are doing here is just we are casting. So this is a typecasting operation, right? So we are taking this image and we are typecasting it into 32-bit floating points. So that's why we're using tf.float32. And then we are dividing this value by 255, right? So everything goes from 0 to 1. and label is unchanged, right? So we are getting image and label, and we are doing these operations on the image, and we're returning the changed image plus label, right? And then yeah, we just uh, map we just map uh, this function on top of the dataset, right? So this is the training part of the dataset. We just map this normalize image function on top of it. Then uh, the other thing is that we set batch size equals 100, right? So train dot batch of 100 basically sets that we are going to use a batch size of 100, and uh, essentially what we'll have then is 600 items, right? Because the training data set has total of 60,000 samples. We're using a batch size of 100, so we'll get 60,000 by 100, 600 samples. The testing part of the dataset has 10,000 samples. So if you look at this DS test, we'll get 100 items, right? Because we set the batch size as 100, right? The next part is the model definition. So here I am using two hidden layers, right? So this is where we are using keras. So we're using this keras.sequential, and model can be defined very simply, just by model.add layer. So the first layer just flattens the input. So we have the standard input for this MNIST is a 28 by 28 image. We flatten it into a 28 times 28784 length vector, right? Then we have one hidden layer. So hidden fully connected layers are called dense in keras. They're called linear in PyTorch, for example, right? So there are different conventions, naming conventions. Uh, yeah, so one hidden layer with 400 units, second hidden layer with 200 units, and finally a dense layer with 10 units. This is the output layer, right? And so here I have one more exercise. So I'd like everyone to try to figure out how many parameters are there, how many trainable parameters are there in this network, right? And I will give some time for everyone to figure out. You can answer in the chat, right? Mm, okay, someone has answered. It's good. Uh, yeah, and I think this is in fact the correct answer also. We will see, right? So here in this code block, we have basically defined defined the network, right? So there's two hidden layers. That is output layer, uh, and then when you call this part, this function model.summary, essentially what it does is that it will give you a summary of the model that you have generated, including the trainable parameters, right? So we run this and it generates, yeah, so it's absolutely correct, 396,210. It's not a difficult problem, right? If you know what these layers are, right? So first layer, so basically there are three dense layers. The first one goes from 784 to 400. So this is 784 times 400 plus 400, right? The weights plus biases. The next one goes from 400 to 200. So this is 400 times 200 plus 200, right? So there are 200 biases and 80,000 weights. So 80,200 total parameters. And finally, the last layer goes from 200 to 10. So the 2000 weights plus 10 biases, so 2010. And if you add all of these up, you end up with 396,210 trainable parameters. And very helpfully, they have also mentioned, how much space is going to be taken up by all of these parameters, right? So this model, whatever we are going to train, is going to take up total of 1.51 MBs of space, right? So the next part, so here is where we will see some of the things that we learned, that we saw, right? So the first thing here, uh, so you can apply different optimizers to your training code, right? And you get you can get varying outputs out of it. Uh, First optimizer that we're going to apply falls under this function called SGD, right? SGD is nothing but stochastic gradient descent. And like I said earlier, stochastic gradient descent and mini batch gradient descent are interchangeably used. In fact, stochastic gradient descent is often used to cover the examples of pure stochastic gradient descent and momentum based optimizations, right? So when you hear stochastic gradient descent, uh, moving on from, like, if you see it written in the paper or something, some literature or something, do not assume that it means that size is equal to 1, because typically people say stochastic gradient descent even for batch sizes greater than 1. In fact, in this particular example, we are using a batch size of 100, right, which we saw earlier. So yeah, so first we will set, stochastic gradient descent, we'll set the learning rate equals to 0.1, and we'll compile the model, right? So here model compilation, also there is something interesting. We set whatever optimizer we are going to use for it, right? Then we set the next thing to set is the model, of obviously, right? Not the model, like, but rather the laws that we're going to train this on. So we are using cross entropy, which we had discussed earlier, I think in the previous session, right? So sparse categorical cross entropy. Uh, Categorical cross entropy just means that the outputs are in the form of class labels, right? The labels are in the form of labels, class labels. Basically, your labels that you are training it to identify uh, exist as like this is a 1, this is a 0, and so on, right? Uh, and the metric is sparse categorical accuracy. So we are generating accuracy as the metric, right? So we have compiled the model. Now there's nothing left to do but to train it, right? So we call model.fit. This is a training data set that we have to pass the number of epochs. We pass the number of epochs, and we pass the validation data for which we are simply using the test data, right? So yeah, so it's going epochs. It has gone through 10 epochs, right? And you can see here the loss, right? So we have gone through 10 epochs. Accuracy, you can see. So first thing here, the first accuracy here is the training accuracy, right? So it is the accuracy on the training data set. And it goes, starts off very low, and then we have reached like 9.92 something, right? And the other part is the validation accuracy, which we have also reached 0.92, right? And here the last plotted is the loss, right? How it goes down, and it kind of gets stuck over here somewhat, right? It is kind of turning into a stagnating kind of thing, right? So this is with simple, this is with just gradient descent, right? So this is just gradient descent. There is no momentum, no energy, nothing else, other kind of optimizer being used here, right? And you see this, right? So it's like 92% on after 10 epochs. So let's do this again. So we'll start here. Compile. Sorry, let's define the model. But here, when we are compiling the model, let's change this, right? So this was simple gradient descent. This is, so the first experiment that we ran was simple descent, right? The second experiment we are going to run right now is momentum, and the third experiment, obviously you can make it out from the name, it is atom optimization, right? So we do momentum, the model compile with momentum. Here momentum term is 0.9, right? And we do the same thing, right? We run this model training again, and let's see what happens. Right, and this here is saying how many milliseconds taken per step, right? Remember that there are 600 batches in the training data set, right? And this count. So here just immediately you can see the change, right? Our convergence in the previous case with simple gradient descent, we had barely reached like 92% accuracy, right, on the training dataset and on the validation as well. But here with momentum, we have reached a much better situation, right? So it's 98.2% on the training dataset. It is 97.4% on the validation or test data set, right? And we are already seeing the fact that the training loss is going below the validation loss, right? So why this happens, what is so a more detailed analysis of this loss curves will be taken up, I think, later on in the course when we talk about bias variance and that those related trade-offs. But yeah, but for now, the important thing is that we changed the we changed the optimizer from simple gradient descent to momentum, and we converged very fast, right? Which was what we had expected also, because momentum is basically making it run faster, right? So that's that with momentum. Let's try now the final experiment here. So instead of momentum, now we are going to use Adam optimizer, which is somewhat later generation of optimizer compared to momentum, right? Uh, More intricate control of the uh, what do I say, of the learning rate, essentially, right? And yeah, so here it goes. Yes, yeah. So Adam optimizer has like three hyperparameters. Typically, there is a learning rate, and there are two other beta 1, beta 2 parameters. Uh, but the papers that the Adam optimizer, uh, like the paper of this method, they had settled on certain values that are good, and those are the ones that are used by default, right? So it is, I think, learning rate is like 1 e minus 4, and beta 1, beta 2 is like 0.99 and 0.999, something like that. And typically when you use Adam optimizer, so this is one of another kind of advantage of Adam optimizer, is that for a first cut decent or good result, you don't need to worry about these hyperparameter values, right? So you can just directly use the default values, and typically that gives a pretty good result. Obviously, if you're trying to optimize, the model performance, you would want to change those hyperparameters and see what happens. But for a first cut, uh, like a estimate of how good something can be, this is pretty good, right? And as you can see, with Adam optimizer, it gets even better, right? So here the training accuracy has gone all the way into 99 point something percent. Test validation accuracy has also improved to 97.8, 97.9 ish percent, right? And this is a of course, this is a smaller improvement compared to what you got by adding momentum on top of simple gradient descent, but this is still an improvement, right? With momentum, you were getting 97.4-ish, and now you're getting like 97.8. So yeah, so this is improved, and here you can see like even more difference, right? So the training loss has collapsed very rapidly, right? Which is because Adam optimizer actually makes the convergence very fast, right? So convergence is happening very fast, and it is significantly below uh, the test loss, right? And why this happens, what happens if we keep on training it like this, right? So all those kind of things will be discussed in later sessions, in later weeks, right? So they fall under uh, bias variance trade-offs and all that kind of things. So yeah, so this is one part uh, of the thing that I wanted to talk about. The other part is, of course, setting this value, right? So we can set this batch values and we can see something interesting, right? So, for example, here in this final run, uh, this took 35 seconds to run this 10 epochs, right? So we can do something. Uh, we can change this batch size. Change this batch size from 100 to 200, and you can see what happens. Right? So now batch size is 200. So this data set contains 300. Where is it? Say 3 items. Something. So we have to go back to it. So get the dataset newly, and we set batch size as 200. So yeah, so previously we had 600 items for the training dataset. Now we have 300 because our batch size is now 200. The total number of samples is 60,000, right? Similarly, for test set, we'll get just 50 items, right? So 50 items times 200 is 10,000. Go to the model and optimizer, and we run this again, right? So let's run this. Yeah. So the first run, of course, is going to take a little bit longer, right? Then we do the next run onwards, we'll see something little better. Yeah. So this again, let's restate the model and then run. Yeah. So here you can see uh, the execution time has become little bit shorter, right? Previously, we saw 35 seconds to execute with batch size of 100, right? For the final iteration, that was like after 2 iterations. Here we are seeing execution time of 29 seconds, right? This is partially because this is not a very capable GPU that I'm running over here, but typically, by increasing the size of the batches, right, you can expect that your execution time will go down until a point, right? So there is a point until which the GPU utilization is maximized, and at that point you will not get any further speed up by increasing the batch size. But until that point is reached, what happens is that the GPUs compute stuff in parallel, which means that if you throw a bigger batch size, the bigger computation is performed in parallel, right? And so your throughput essentially increases, right? So the amount of time it takes to compute for a batch size of 200 is not twice the amount of time it takes to compute for a batch size of 100. In fact, if the GPU is capable enough, the amount of time it will take for the larger batch size will be very close to the amount of time it takes for the smaller batch size, right? But of course, when you have a larger batch size, you have fewer number of iterations to run, so it runs faster, right, than the smaller batch size. But also, at some point, uh, you also start having this problem of the extreme. So we saw the extreme case with vanilla gradient descent, where you were updating it only once for the entire data set. So if you try to increase the batch size too much, then you start getting that problem as well, right? So you are getting kind of fewer and fewer uh, you start getting fewer updates, and that hurts the convergence of your model, right? So it might take longer in terms of epochs, right? So it might take longer in terms of epochs, but each epoch is faster, so maybe it takes the same amount of time, right? You don't really know. So these are kind of empirical problems. There is no kind of theoretical answer to which will take more time, which will take less time, right? But yeah, if your convergence is not being hurt by using a larger batch size, and if it is still kind of if the GPU or whatever you're using is not completely maxed out, you can increase the batch size, it will run things faster, right? So yeah, and of course stochastic gradient descent is on the opposite end of this discussion, where if you're computing, I mean stochastic in the sense how it is defined in the material. So if you're computing gradients for every sample separately, it is going to take a lot of time, right? So if you reduce the batch size, for example, if you reduce this batch size from 20 to 200 to 20 or 200 to 50, let's say, uh, it's going to take much longer to compute than before, right? Because it has to compute, multiple. Yeah, I'm sorry, to from here. Yeah, yeah. So with batch size of 50 now, we have 1200 uh, things, 1200 batches to compute per epoch, and that's what it is. Right. So basically, what I'm trying to say is that there is a sweet spot in terms of the batch size where your computation is also optimized, speed of computation is optimized at the same time. The convergence of the network is also kind of optimized, right? And the way you find this basically is by going, taking like trying out multiple different batch sizes and seeing which one works best for you. Yeah. So with batch size of 50, it took like whatever 53 seconds, right? But our convergence is pretty good, right? So we got even a little bit better than what we had gotten with batch size of 100. So that's what happens. Okay, yeah, 48 seconds, right? So, like I said, it becomes slower, but you get better convergence, slightly better convergence compared to batch size of 100, which was itself slightly better convergence compared to batch size of 200, right? With batch size of 200, we are seeing validation accuracy of 0.975 or something. With 100, we are seeing 0.978. With batch size of 50, we are kind of crossing this 98% threshold, right? And this thing is whatever it is, right? We will see. So if we kind of extend this even further, what happens? Uh, we'll see, right, later. So yeah, so that's all. So that's the end of the whatever I wanted to discuss today. If you have questions, you can ask. Uh, Otherwise, you are free to leave. Which one is best? Uh, the standard in literature is to the standard in literature is basically to use HGD with momentum, right? Sometimes people put NAG, right? Uh, Alternatively, you can use Atom, right? Atom, you don't have to deal, you don't have to worry about the the what do you call it, hyperparameters so much, right? So you can do it with the default parameters, and it will give you pretty good uh, optimization. With SGT, you have to tune the learning rate, right? So if you tune the learning rate properly, then SGT with momentum is very good. If you don't want to tune hyperparameters, then Atom is good. Uh, yeah, uh, there seems to be no further questions. If there are no further questions, I can leave. I'm going to end this call then. Okay, thank you.